If you asked your AI assistant to check the local weather for you this morning, there is a very real, um, a mathematically terrifying chance that it also quietly read your private emails.
Yeah, and probably scan your financial documents while it was at it.
Exactly. And mapped out your network directory. And the scariest part about all of this, it didn't even have to hack you to do it. It just, asked nicely.
Right. I mean, the system essentially just held the door open and invited the threat actor inside, all in the name of seamless integration.
Welcome to today's deep dive. We are unpacking a highly critical, basically flashing red cybersecurity report straight from the National Security Agency.
And we're going to examine a foundational piece of technology called the Model Context Protocol, or MCP.
Yeah, but before we get into the weeds of how this protocol is fundamentally rewiring the internet, a massive thank you to our sponsors, www.vibehack.dev and CISOmarketplace.com, for making this deep dive possible.
So let's set the stage a bit. Anthropic released MCP as an open source framework back in November 2024.
And it basically caught fire, right? Like overnight.
Oh, absolutely. It rapidly became the de facto standard for how AI services communicate with one another.
So for you listening, when you tell an AI to, say, plan a trip, and it autonomously talks to a flight API and then a calendar, and a Visa database MCP is the middleware making that magic happen.
But the NSA is sounding the alarm here. They are stating that MCP's rapid growth has vastly outpaced its security,
Leaving massive structural vulnerabilities just, wide open for exploitation.
To understand why the NSA is so concerned, we really have to look at the philosophical tension at the heart of MCP, because this isn't just about a missed line of code or a simple patchable bug.
Right, it's bigger than that.
Exactly. We are looking at a foundational clash between two opposing paradigms, agentic autonomy versus zero trust security.
Which are basically opposites.
They are. Traditional security zero trust, it requires strict predefined boundaries, but AI agents require fluid dynamic discovery to actually be useful.
I have to push back on this right away, though. I mean, Anthropic has some of the most paranoid, top-tier AI safety researchers on the planet.
They definitely do.
So I absolutely refuse to believe they just, forgot to implement basic security checks.
Yeah.
There has to be a design reason for this. Were they just prioritizing developer adoption over security to win the protocol war?
Well, it is less about forgetting and more about the inherent friction of the architecture they were trying to build.
Okay, what do you mean by that?
If you want an ecosystem where an LLM can spontaneously discover a new tool, figure out how to use it on the fly, and then execute a multi-step workflow without the user having to approve every single microtransaction, you have to loosen the traditional constraints.
So they built MCP to be radically flexible.
Yes, they release an underspecified design to encourage rapid adoption, but the trade-off for that absolute frictionless environment is that the orchestrator must inherently trust the tools it discovers.
Which brings us to what the sources call the structural flip. Now, I want to make sure I have this straight, because in traditional web architecture, we have a unidirectional trust model, right?
Yeah.
Clients request data and servers provide it. But MCP completely inverses this relationship.
It does. The protocol actually expects the servers to query and sometimes execute actions for the connected clients.
Wait, really?
Yeah. You are essentially allowing the back end to drive the front end's behavior based on dynamic, unverified context.
That inversion is wild to think about in practice. I mean, it would be like going into a high-end bank, asking the teller for your account balance, and the teller is technically allowed to reach across the counter, take your house keys out of your pocket, go to your home, check your filing cabinet to verify your identity, and then come back to hand you a receipt.
That is a terrifying but very accurate analogy. You've completely surrendered the boundary of execution.
And that surrendered boundary creates attack paths that traditional security tools simply aren't looking for.
Exactly. Because MCP flips the engagement rules, you are handing the keys to your digital environment over to an orchestrator that basically operates on blind faith.
Let's look at how this manifests technically.
Okay, where do we start? Access control. Yeah, starting with access control. The protocol itself does not mandate authentication. Many developers implementing MCP servers just omit it entirely.
Which is exactly where organizations really need to be leaning on resources like CISOmarketplace.com for vetted infrastructure solutions, because relying on the default protocol behavior is clearly a recipe for disaster.
It really is. But even if a developer does implement authentication, there is absolutely no built-in support for role-based access control or RBAC.
And that absence of RBAC has to be devastating in an agentic workflow.
It's a nightmare. In standard database administration, we rely on CRD operations, create, read, update, delete. Those are highly distinct privileges.
Right, you might want someone to read a file, but definitely not delete it.
Exactly. But in MCP, those granular boundaries frequently just collapse. The orchestrator doesn't distinguish between the permission to read an email and the permission to forward or delete it.
So if the agent can touch the data, it can often just manipulate it entirely.
Yes. Once the agent is authenticated, it essentially has super user access to whatever context it was granted.
Wow. But the way they handle the actual session life cycles seems just as negligent to me. The sources mention MCP servers rely on OAuth 2.1 bearer tokens, but the core specification completely ignores protocol-level token lifecycle management.
Which leads to what we call the creation of immortal sessions.
Immortal sessions, like they just never expire.
Basically, yes. Without mandated expiration, or forced refresh intervals, or a standardized revocation process, an OAuth token becomes a permanent skeleton key.
Oh, man.
Yeah. If a threat actor intercepts that bearer token, they don't even have to use it immediately. They can wait weeks, hijack the valid session, and replay old messages to trigger unintended actions.
And they can impersonate legitimate clients indefinitely.
Right. And because the session never officially expired, the intrusion doesn't trigger standard anomaly detection alerts.
And because we're talking about AI orchestrators here, the data being passed around with these immortal tokens isn't just standard JSON key-value pairs, right? It's often serialized natural language or highly complex prompt structures.
Yes, and that is a massive issue. When MCP transmits structured objects between the client and server, it often lacks strict validation schemas.
Meaning what, exactly?
Meaning you are feeding unsanitized, dynamically generated data directly into an LLM's natural language parser. We've seen this movie before with classic insecure deserialization vulnerabilities, but now it's adapted for neural networks.
Wait, let's pause there because that implies the AI doesn't know the difference between a system command and a user's raw text.
It often doesn't.
If there's no schema enforcing this is data versus this is an instruction, an established, trusted MCP server could completely alter its capabilities in the background. It could change the data it accesses without ever prompting you for informed consent.
Exactly. The dynamic nature of the protocol allows a server to update its tool definitions on the fly.
Give me an example of how that would look.
Well, you might install a local MCP server that advertises itself as a simple weather checking tool. Tomorrow, that same server updates its internal manifest to include file system read access.
And the user doesn't know.
The user has no idea. The orchestrator sees the new tool, trusts it, and begins utilizing it without breaking the session or alerting the user.
This isn't just theoretical red teaming either. The sources detail how threat actors have already weaponized these structural gaps into devastating real-world exploits.
Yes, the GitHub exploit is a perfect example of that access control failure we talked about.
Right. Users integrated an MCP server for GitHub, granting it access to automate their repository management.
But because of that lack of granular RBAC, permissions couldn't be scoped to specific repositories. The MCP tools had blanket access across the user's entire GitHub environment.
So a compromised tool in the chain didn't just read the code it was supposed to be working on. It silently accessed highly sensitive proprietary code from the user's private repositories and then published it directly into public repositories.
Exactly. And the users had absolutely no idea a massive intellectual property breach was happening because the AI orchestrator thought it was just executing a valid authorized workflow.
The orchestrator acted exactly as designed, which is the terrifying part.
It is. But the WhatsApp exploit shows an even more sophisticated manipulation of this architecture.
Oh, this one is wild.
Yeah, researchers analyzed a popular, trusted, third-party MCP agent that was designed to enhance WhatsApp chat capabilities, and they actually managed to introduce a malicious MCP server into this agentic system.
I read the breakdown of this in the report, and the methodology is brilliant in a very dark way. Walk me through how the malicious server coerced the client, because it wasn't a brute force attack.
No, not at all. It was basically psychological manipulation of the AI. Because the MCP client connects to both the trusted WhatsApp server and the newly introduced malicious server, the orchestrator has to decide how to rack tasks.
Right.
The malicious server manipulated its own tool descriptions. It effectively convinced the orchestrator that it was the most efficient route for handling message data. So it bypassed user approval entirely and pulled message data directly from the WhatsApp server.
But the twist, the real digital bait and switch, was how it hit its intent.
Yes. When the malicious server was first installed, it didn't do anything malicious. It advertised a totally benign instruction.
So it just operated normally,
Yeah.
building trust within the orchestrator's routing logic.
Exactly. It wasn't until the second time it was invoked that it switched its instruction payload to steal the data.
The orchestrator's blind trust in dynamic tool discovery is the root cause there, right? The system just assumes that a tool's behavior today will match its behavior from yesterday.
Which introduces a massive logistical nightmare. Think about it. If you tell your AI orchestrator to use the data analysis tool, how does the system actually know which specific tool to call if there are 5 different tools with similar descriptions?
That's a good question. How does it resolve that?
Well, resolving namespaces in dynamic environments is inherently vulnerable. MCP clients frequently lack the ability to specify unique, cryptographically verified tool identifier.
Ah, I see where this is going.
Yeah, if an orchestrator automatically resolves tool names based on text matching, an attacker can simply name a malicious local module the exact same thing as a widely used, legitimate tool from a public registry.
A naming collision.
Yes. The orchestrator gets confused by the duplicate names. And if the local malicious module logs first or has a more aggressive description, the system defaults to it.
Wow.
The attacker successfully hijacks the execution flow simply by giving their malware the right title.
So a single compromised tool is dangerous enough. But the urgency of this NSA report stems from what happens when you string these tools together into multi-agent workflows.
Because when one tool gets poisoned, it instantly weaponizes the next tool in the chain.
And this is exactly why developers need to be building secure foundations from day one, using platforms like www.vibehack.dev to anticipate and mitigate these cascading failures in complex applications.
That cascading failure model is critical to understand. Let's break it down. In a multi-agent system, Agent A completes a task, generates an output, and passes that output as context to Agent B. The architectural flaw is that Agent B treats Agent A's output as an inherently trusted, sanitized input.
It's essentially money laundering, but for malicious code. The dirty instruction gets washed through a legitimate, trusted node Agent A, so that by the time it reaches Agent B, it looks like a clean, authorized command.
That is a perfect way to visualize it. The attacker uses semantic manipulation. They embed malicious instructions within what appears to be a standard text output.
And because MCP lacks those strict schemas to delineate data from executable commands, Agent B just ingests the text.
Right, and its parser misinterprets the hidden string as an executable prompt. The prompt injection cascades down the chain, elevating privileges at each step until it results in full data exfiltration.
But we aren't just talking about data leaks either. We are talking about hostile remote takeovers. The report highlights CVE 2025-49596.
Yes, that was a critical vulnerability.
Found in the MCP Inspector tool, which ironically is the exact software developers use to test the security and functionality of their MCP servers.
Yeah, the irony is thick there. The inspector tool accepted unverified inputs from the servers it was testing. Malicious actors realized they could send crafted messages back to the inspector that triggered remote code execution, or RCE.
Wow. So as the industry races to build autonomous AI toolchains, developers are basically abandoning basic, decades-old security hygiene.
Exactly. And if an attacker achieves RCE, the game is over. They own the host machine.
Okay, so knowing that the underlying architecture is primed for cascading prompt injections and RCE, how do organizations actually put guardrails on this before deploying it into production? I mean, we clearly can't just bolt a firewall onto it and call it a day.
No, a firewall isn't going to cut it. The NSA's containment playbook focuses on aggressive compartmentalization.
Okay, that's step one.
The first directive is establishing strict boundaries through data classification zones. You can no longer rely on a single monolithic agent to orchestrate everything.
So you have to, like, air gap the financial vault from the public lobby.
Essentially, yes. Tools that pull public data, like weather APIs or stock tickers, they operate exclusively in a low-trust public zone.
Makes sense.
But tools that access sensitive health records, internal financial data, or private GitHub repositories, those must be explicitly segregated into high-trust zones.
And they can't talk to each other.
Right. The orchestrator should physically lack the network routing to pass context between those zones without human-in-the-loop cryptographic authorization.
But even within those zones, you still can't trust the application layer, right?
Which is why the second directive mandates sandboxing the execution environment at the OS level. Every single MCP tool invocation must be treated as a highly volatile, high-risk action.
So what does that look like practically?
Organizations need to deploy frameworks like app containers, seccomp, Aparmer, or Linux to isolate the execution context.
Oh man, I can hear developers groaning from here. Applying strict Salinas profiles to an AI agent that is supposed to be dynamically discovering new tools sounds like an operational nightmare. It inherently breaks the fluidity that MCP was designed to provide.
It absolutely adds massive friction. It's a pain. But if a tool gets compromised and triggers an RCE, that OS-level sandbox is the only thing preventing lateral movement across your network.
Right, it stops them from pivoting to other machines.
Exactly. Furthermore, you cannot allow these agents to communicate with the open internet unmonitored. Outbound connections must be routed through filtering proxies like Squid and integrated with enterprise data loss prevention solutions to catch exfiltration attempts in real time.
Okay, so we are putting heavy filters on the exits and isolating the processes, but we still have the issue of the actual protocol messages flying back and forth without robust ID checks or integrity validation.
Yeah, that's the next layer. Since the MCP specification doesn't enforce message integrity, developers must manually extend the protocol. You have to inject cryptographic signatures directly into the JSON payloads.
So every message is signed.
Every single message passed between a client and a server needs to be cryptographically bound to its specific time and context.
So you're adding expiration timestamps and replay protection metadata to the JSON itself. That way, if an attacker intercepts that immortal OAuth token we talked about earlier, and they try to resend an old command to trick the system.
The cryptographic signature will fail validation because the timestamp is stale.
Got it. You are manually hot-wiring zero-trust principles onto an architecture built for autonomous trust.
That's exactly what you're doing.
But implementing all of this, the OS sandboxing, the cryptographic payloads, the isolated zones, that's crucial for deploying new systems. But it doesn't address the massive looming threat of what is already inside the house.
Shadow IT.
Yeah. If a developer can pull an MCP server from a public registry in the 3 seconds just to test a workflow, how does a security team even know if a vulnerable, unauthorized MCP instance is actively running on their local network right now?
That is the defining challenge for network defenders in this ecosystem. You cannot secure shadow IT. The NSA report outlines a specific arsenal of scanning tools required to hunt these shadow MCPs.
What are the tools?
Things like MCT scanner, ramparts, cyber MCP, and proximity.
And what are we actually instructing these tools to look for? Because an MCP server just looks like generic network traffic most of the time, doesn't it?
It does, which is why security teams must configure these tools to aggressively hunt for 4 specific failure conditions. First, unauthenticated instances, basically servers operating with no login or token requirements.
Okay, that's one.
Second, vulnerable servers running outdated protocol versions associated with known CVEs. Third, unauthorized deployments instances that were spun up outside of the approved IT change control process.
Right, the developer just running it locally.
Exactly. And fourth, unregulated internet connectivity, where an internal high-trust tool has an unmonitored, wide-open path to external IP addresses.
But there's a massive operational catch here, isn't there?
Yeah.
MCP servers don't just sit on standard, predictable ports like web traffic on port 443.
No, they are notoriously dynamic. They change their network ports constantly based on available resources and orchestrator demands.
It's like playing digital whack-a-mole. If you run a port scan on Monday, the results are completely invalid by Wednesday.
Exactly. Because of that dynamic port behavior, point-in-time scanning is completely useless. Organizations have to transition to continuous periodic scanning and rely on differential reports.
So comparing today to yesterday.
You must constantly compare the network baseline of today against yesterday to identify anomalous, modified, or suddenly relocated services. The vigilance required is immense.
It really requires a fundamental shift in how we view these tools. Let's distill all of this. The Model Context Protocol is an undeniably powerful engine. It is the connective tissue driving the future of seamless AI automation.
It really is.
But the exact characteristics that make it revolutionary, its radical flexibility, its dynamic discovery, and its inverted trust model are currently its greatest liabilities. Until the protocol specification matures to enforce security by default, securing AI workflows relies entirely on the rigorous, highly manual interventions of developers and network defenders.
Right. We just have to stop romanticizing AI agents as infallible, helpful assistants. From a systems architecture perspective, they're highly privileged, untrusted inputs that require constant cryptographic verification.
Absolutely. A massive thank you once again to our sponsors, www.vibehack.dev and CISOmarketplace.com, for supporting the show and allowing us to bring this level of analysis to you.
It's been a great deep dive.
Before we wrap up, I want to leave you with something to consider. something that goes beyond just patching the vulnerabilities. As we integrate these autonomous multi-agent systems deeper into our lives and businesses, we are approaching a massive legal gray area.
Oh, definitely.
If an AI orchestrator dynamically discovers an unauthorized MCP tool, bypasses your intent through a naming collision, and ultimately commits a crime like exfiltrating proprietary data or executing a fraudulent financial transaction, who is legally at fault? Is it the developer who left the protocol open, the orchestrator that made the unverified handshake, or you, the user, who simply typed the prompt? As the technology outpaces the architecture, it might just be outpacing our laws too.